Hi, this is Sumith Makam. I work for NetApp in FileSystem group. I have been in this group for the last 15 years, working primarily on space management, volume management, consistency point, file systems, etc. Of late, I have been working on designing cloud solutions for file systems. Today, I'm going to talk about how object store can be used in backing up the data and disaster recovery workflows, and how analytics applications can also leverage the data that is backed up on the object store. As part of this talk, we'll do a small introduction of object store. For most of the crowd here, this will be a recap rather than an introduction. Next, we'll talk on file systems and object store. Few file systems use object store to store their primary data, whereas few use object store to tear out cold data from the primary nodes. We'll also talk about how file systems can be laid out on object store, advantages of building file systems on top of object store, and design aspects that needs to be considered. In this talk, we'll mainly focus on how object store can be used by file systems in other workflows like backup restore, secondary storage solutions, disaster recovery. We'll also present high-level solution of above workflows. At the end, we'll present a few use cases and optimizations that are still pending around file system and object store. Coming to the benefits of object store: optimized cost, ease of use, scalability, and rich feature set. These are the primary benefits of an object store. As mentioned, one of the main benefit is cost and ease of use. AWS standard tier charges 5 cents for 1,000 put and list operations and 0.4 cents for 1,000 get requests. Because of this low cost, object store is used in various products and workflows. Leveraging the cost aspect, few file systems tear out the cold data from the performance tier. This will help in reducing the cost of expensive SSD drives on the performance tier. Other than tiering, object store can also be used to back up complete file system. Most of the critical applications will have replication enabled and take regular backups to secondary nodes. Instead of having a dedicated secondary nodes, object stores can be used in those workflows to back up data. This will reduce the overall cost of a secondary solution. We'll talk in more detail about this on how data can be backed up and used in the secondary storage. Ease of use comes from the fact that applications need not go through a lot of configuration hassles to configure object store to store its data. Once the bucket is configured, access will be over HTTP. In contrast, applications which has to use EBS drives have to be attached to EC2 instance, and they can only be accessed in the same region. Moreover, the capacity will be limited. Once attached, even if the storage is not used or there is not much IO on the drive, the space will still be built. But in case of object store applications, object stores can be accessed across various regions, and the charging is also based upon the usage and storage that is used rather than the provisioned space. Coming to the scalability aspect, in case of EBS drives, they can only go to certain TB. But the applications which needs a lot of petabytes of storage, they cannot be accommodated on EBS drives. So object store can be used in those for those applications to store a lot of unstructured data. And some of the file systems which have a requirement to have a lot of backup data, they can also be accommodated on object store. Last but not the least, object store comes up with a rich feature set. We'll talk about each of the features in some detail. Resiliency. Any data returned to the object store can be replicated to a different bucket. There is a configuration at the bucket level which can be enabled, and once it is enabled, all the data that is getting returned to the bucket will get replicated. This will provide a higher level of resiliency against any storage failures. Cross-region replication. Apart from the resiliency within the same region, if some applications require an availability across regions, then cross-region replication can be enabled at a bucket level. Once it is enabled, all the objects that are getting returned to the object store will be backed up to the other region automatically. Tagging. Objects can be tagged and different policies can be associated with each tag. Based on the policies, different actions will be performed on the objects. For example, to tear out an object after a certain amount of time, a new tag can be created and it is associated for the objects which needs to be teared out. Once the objects are tagged, admin can go to the AWS console and associate a policy against the customized tag, saying that tear out all the objects with this tag after a certain duration of time. So once it is configured, whenever the objects gets returned to the object store, they get automatically tiered out to a slower tier after the configured amount of time. Versioning. There is a new feature called versioning. Once it is enabled at a bucket level, any overwrite of an object will not result in deleting the old object, and then any overwrites of an object will result in creating a copy of the object rather than overwriting it. This helps in some of the use cases where some customers wants to have a protection against tampering of the data. Immutable objects. Object store also provides a functionality to prevent deletion of objects for certain interval of time, which is configurable again at a bucket level. This helps to comply with certain policies where data is supposed to be retained for certain amount of time. Tiering. Most of the hyperscalers provide cost-effective but slower tiers. For example, AWS has Glacier and Deep Glacier. Certain objects can be tagged with a policy saying that tear out this particular object after a certain duration of time to slow tiers. Once it is configured, tiering will automatically happen. Now we'll present specifics about how object stores are used by file systems. Few file systems just use object store to store data as a key value pair without any specific layout. Cluster file system is an object file system with a key value pair. But traditional file system layout can also be built on the object store with a directory hierarchy. In this layout, all other file system elements can also be stored like icons and streams. Other benefits of having a traditional file system and object store is to use buckets for a secondary solutions. If primary data is backed up in traditional file system format, the same set of applications that are used on the primary can be run on the secondary as well. Benefits. Once the data is backed up to object store, it can also be used as a cost-optimal DR solution, which we'll talk in the next set of slides. As stated earlier, object store also will help, having an object store will also help in scaling the storage needs of a secondary node without much effort. Design aspects. Some of the design aspects that needs to be considered in file system while using the object store to store data. It is very common to file system to overwrite a lot of data, but this requires an extra handling in case of object store. Overwrites to an object are allowed, but the guarantee provided by the hyperscaler is called an eventual consistency. That is, if an object is overwritten, readers can get a older data for certain duration of time. After certain duration of time, object store will start returning newer data. But recently AWS started supporting a stronger consistency, that is, returns a newer data once it is overwritten. Because of the eventual consistency, all the applications have to ensure that the data that they are reading is latest. So to overcome this issue, most of the applications never use to overwrite objects. As true with managing any storage space, file system should also address and manage the object space. So in case of disks, they are numbered, blocks are numbered as a disk block numbers. In case of object store, combination of a string and sequence number is commonly used to address a given object. Also, file system has to keep track of the objects that are freed, so that periodically those objects can be freed up in the object store. So garbage collection becomes a primary or important module in any application which handles object store. Other important aspect which can play a major role is in the performance of the object store is choosing the right object size. Selecting a smaller object size can result in having too many put and get requests, which can increase the cost of the overall solutions. On the other hand, having a bigger object size will incur a performance penalty, as reading a smaller amount of data also can result in reading a larger chunk of data. So there should be a balance on, based upon the application, what should be the size of the object. Typical object sizes that most of the applications use are like 2 MB or 4 MB. Again, object store can also, other aspect that needs to be considered is the concurrent access. That is, if the same object store is being accessed by multiple applications from same node or two different nodes. Object store can be considered as a central storage server, and applications can access it from different nodes at the same time. So applications have to take care of concurrent access to object store by implementing logs at the application layer. This is similar to how file systems take reservations on dual port drives to ensure only one node can access the disks. Without this login mechanism, if two applications tries to write to the same object, they can end up corrupting the data. The next design aspect that needs to be considered is minimizing the number of metadata reads. Any file system will have some metadata associated with its data. That is, whenever some data has to be read, before reaching that data, some extra metadata blocks have to be read. So given the high latencies that are there in the object store, layout of the file system should be designed in such a way that minimum number of metadata blocks have to be read before data can be read. So this is one of the important aspects that needs to be considered because of the S3 latencies. Again, as S3 latencies are generally in the range of 20 to 80 milliseconds, applications should have enough parallelism, and they should also have caching implemented in the application, so that frequently read blocks will be cached locally and can be served from the local cache rather than always reading from the object store. Other aspect is the network delay and tolerance. File systems are primarily designed to read and write data from the disks which are present in the disk shelves. So they wouldn't expect long delays and much of intermittent failures. But access to object store can be over a public network where there can be network delays and a lot of intermittent errors. Applications should expect these delays and intermittent errors and be tolerant to such errors by having some retry logic in the applications. So this retry logic should be there before. If without this retry logic, with a intermittent error, the applications can end up returning an error to the clients. So rather than that, keeping the network delays and errors, intermittent errors in view, applications should have the retry logic themselves. So after retrying for certain amount of time, if the same error persists, then it's okay to run an error to the clients. So, but there are certain type of errors which are called fatal errors, like object not found. In those cases, it's okay to return an error as soon as error to the client as soon as error is returned by the object store. Here is the overview of a backup restore solution. Node at site A will be regularly backing up data to object store. I mean, here consider there is a node at site A which is regularly taking the backups to S3 bucket. Unlike traditional backup systems, data here need not be backed up to a separate dedicated node. Instead, it can be backed up to an S3 bucket. As with any backup solution, data will be backed up at regular intervals, and only incremental changes will be backed up. Again, data on this primary node would have been deduplicated and compressed. So there could have been a lot of storage efficiency achieved on the data that is written on the on this node. So while backing up, it should be all the storage efficiency that was achieved should be preserved in the S3 bucket. If storage efficiency is not preserved in the bucket, amount of data can get bloated up in the bucket, as well as whenever it is restored, it gets bloated up on the other node as well. So preserving your storage efficiency during backup becomes an important design aspect that needs to be considered for backup solutions. Once data is backed up, the backup data can be used. Backup data can be used to be restored on any other node on which is present on any other site. So the backed up data the complete backup of the file system can be restored, or if some application wants to just restore a single file or a single directory, that also just that particular directory or a particular file can be restored to a different node. Other aspect is if the data is encrypted and stored on the primary node, either the encrypted data can be backed up if the same key, or data can be decrypted and then plain text can be backed up, or data can be backed up by encrypting with a different key as well. Here is the comparison of traditional secondary solution and object store based secondary solution. On the left side, you see a traditional secondary solution wherein primary site, there are a bunch of nodes there are a bunch of nodes on the secondary site as well. So here, just for the illustration, we have listed every node on the primary is backing up to a different node on the secondary. Typically, it need not be one-to-one mapping. It can as well be many-to-one mapping, as in multiple nodes on the primary side can keep taking a backup to only single node. Coming to the object store based secondary solution, as mentioned in the previous slide, the primary site all the nodes on the primary site can keep taking backup to the bucket. Once the data is backed up, there could be some cloud data services can be spun off, which can read data from the bucket and do some analytics applications can read data from the object, or some AI ML applications can read the data to do some modeling. Apart from that, we can also build file indices by reading the data from the bucket. So these file indices can be used whenever a single file has to be located in the complete backup, which by locating that single file, if somebody wants to restore that file, knowing the location of that single file is important. So these file indices need to be built in order to support a single file restore or a directory restore. Extension to the backup solution mentioned in the previous slide, data once backed up can be used to serve data whenever the primary node goes down. So all these nodes are backing up the data to the object store. So apart from spinning up the applications in order for cloud data services and to build a catalog, this backed up data can also be used whenever the primary node goes down. If the primary node goes down, new EC2 instance can be instantiated in cloud, and S3 bucket can be configured in this EC2 instance to read data. Once bucket is attached, data can be read from bucket and can be stored in the local EBS drives. Once the data is restored from the bucket and stored on the EBS drives, applications can be started, and applications can start reading the data from local EBS drives, and then applications can keep running. But there are two flavors of restores that can be supported based on the RTO requirements. What is an RTO? RTO is a recovery time objective, right? This is the time taken to resume an application on the secondary site once the primary site goes down, right? So why do I say that it is based upon the RTO, right? So if an application wants to access the data, or if an application cannot take, if an application needs to access data, cannot take a downtime, then what it implies is as soon as primary site goes down, applications needs to access the data. So in that case, we will not have a liberty to restore complete data to the EBS drives, because restoring the data to EBS drives can take a lot of time. So in those cases, what can be done is only certain amount of high-level metadata can be restored to local drives and applications can be started. So now applications will have a read-write access to the data from the EC2 instance. As only certain amount of metadata data has been restored, if applications ends up reading some data which is not yet restored, then those reads will be, that data will be read from bucket and then it will be served. So this will have some latency. Applications will incur some latency here in this case. So this is called as an on-demand restore. But if the applications do not have any stringent RTO requirement, but they are latency sensitive, means that they cannot tolerate higher latencies. Right? In those cases, complete data can be restored to EBS drives and then applications can be started. This is called a full volume restore. Here is the DR solution overview. This is an extension to previous 2 slides or a secondary solution that was covered earlier with an additional step of incremental restore. We'll get to the details of what incremental restore is. Let's go over of this particular workflow in little more detail. So here 1 and 2 are application accessing the local storage for their reads and writes. And the 3 is where these applications will keep taking the backup to the S3 bucket. At 4, say if primary site goes down, as mentioned in the previous slide, a new EC2 instance will be instantiated and this bucket will be configured to it, and then applications can be started. Before applications can be started, certain amount of data or the complete backup has to be restored to the local EBS drives, and then this applications can be started. Now, because now applications can, whenever the applications read data, the data will be read from the local EBS drives, or data will be read from bucket if it is not yet restored. Right? But any new writes that happens, that application does, will be written locally. Right? Whenever as the application keeps writing new data, it will all be written to the local EBS drives. As new data is being written, it also makes sense to back up that data regularly to the object store. So you can, if the primary node is down for a longer time, this secondary site can back up multiple snapshots to the bucket. What it implies is, if the primary node comes back online, all the backups that were done on the DR side have to be restored back to the primary, so that primary can come back up and then serve the applications. So restoring all the changed data on the DR side is called incremental restore. So this is the step 7, which is an additional step compared to the previous solutions that we have covered. So if the primary site comes back online, we'll have to do an incremental restore, which is like transferring all the newly changed backup data that is backed up onto the primary site. Once it is done, applications will come online on the primary site, and applications will start working. As I conclude this presentation, here are a few enhancements that can be done on top of current solutions. In the secondary solution, we discussed about 2 types of applications. That is, applications with smaller RTO but tolerant to higher latencies, and other set of applications which can tolerate higher RTO but latency sensitive. But there are certain applications which require a smaller RTO and also cannot tolerate higher latencies. So currently there is no easier or cleaner solution to cater such applications in the disaster recovery workflows. The other point is, multiple volumes can keep taking their backup to the object store. There could be a lot of deduplicated data in all of these backups. So object store usage can be reduced if data across all these backups can be deduplicated. So the third one is solutions mentioned in the above slides can also be used in order to migrate data from on-prem to cloud with some more enhancements. This is all I have for today. Have a nice day and thank you.